Thanks for the introduction. And my name is Panpan. I'm here today on behalf of Xiao to present the work, The Impact of the Interfacial Layer on Silicon Oxide-Based Flexible Cross-Point RRAM. And here is the outline. First, I will give a short introduction and to mention the motivation and the recent research progress on this topic. Next, I will move to the fabrication process, and following are the physical and the electrical characterizations. Finally, we will come to the conclusion. 3D cross-point technology is a major breakthrough in memory process technology, and it has several advantages. For example, the high speed. It has been demonstrated to 1,000 times faster than NAND, and also high endurance. It can operate up to 10 to the power of 12. 10 to the power of 12 cycles. And also, it can be integrated with ultra-high density. And RRAM, as an emerging non-volatile memory technology, has been demonstrated to be suitable to applicate in such architecture. To fabricate the RRAM just mentioned, a lot of switching materials has been investigated, something like the hafnium oxide and also tantalum oxide. But among a lot of switching materials, silicon oxide has been considered as one of the most promising one because due to the several advantages. For example, the huge abundance in nature and the seamless compatibility. Also, it has a wide band gap. And also, due to its excellent flexibility, it can also create oxygen vacancy at room temperature. Let's go through several recent progress on silicon oxide-based RRAM. From all the work listed here, we can clearly see that the silicon oxide-based RRAM has been reported frequently these years, but we also face several significant challenges. For example, the silicon oxide-based flexible RRAM are rarely reported, and all of the work listed here, you can see it suffers from a larger complex current level, and also for the 3D cross-point architecture, we need not only the RRAM, but we also need a selector. And but there is no silicon oxide-based selector reported. And our work reported here will target at such issues. The process steps are schematically shown here. First, the captain substrate will be cleaned using the IPA solution, and then the bottom electrode was patterned, and 60 nanometer 9 layer was deposited, and then the cross-point bar was patterned, and 10 nanometer switching material, let's say the silicon, was deposited. After that, 4 nanometer P interfacial layer was deposited on one of the sample, and this sample will be denoted as D2. For the reference sample, without the P interfacial layer will be denoted as D1. Finally, the top electrode will be patterned and 60 nanometer 9 layer deposited. The lift-off process was done to obtain the final devices. From the figure A was captured from the camera, you can clearly see the whole flexible substrate and the inside. And the inside is a image, zoomed-in image showing NOS. From the optical image in figure B, you can clearly recognize the whole crossbar area is approximately 5 times 5 square micron. And next, we first introduce the physical characterization of this device. From figure A, we can clearly recognize a 3.2 interfacial T oxide layer, I mean the bright one. And then a 10 nanometer silicon oxide layer also formed the more darker one. And the figure B show you the figure B shown here to confirm the elemental. This is XPS profile to confirm the elemental composition of the silicon oxide. And next, we come to the resistive switching behavior. For fair comparison, the CC level was kept at 500 nanoampere for both cases. And from the left figure, which is the D1, we can clearly see that the D1 shows high non-linearity factor, which is larger than 22, and also high rectifying ratio, which is larger than 4 times 10 to the power of 3. And we can also conclude here the T interfacial layer, the impact was the higher leakage current and also lower forming voltage in D2, since it has been decreased the forming voltage from 2.7 to 2.1 here. And also another important you can observe is that the reset current is in D2 is much higher than in D1. So down here, the bipolar resistive switching in D2 has been achieved, and it has a large memory window and also a low CC level. We also investigate the conduction mechanism. Here is the linear fitted of long I versus root of voltage. And this figure can confirm that the Schottky emission is the dominant conduction mechanism in LR state. And the extracted Schottky barrier for D1 and D2 is respectively 0.78 and 0.52. So the Schottky barrier is lower in D2 than in D1, then you can expect a higher leakage current in D2 than in D1. For better understanding, the band diagram is illustrated here. And since the T interfacial layer has a higher Gibbs free energy, so the T interfacial layer will take oxygen from the switching material, or let's say the silicon oxide, and this will make the switching material more defective, and thus the leakage current will increase and the forming voltage will decrease. And also due to the presence of the T interfacial layer, since it has a similar election affinity with the top electrode, with the top metal electrode, so you can expect a lower Schottky barrier will form at the top interface than in D1. So the injected electrons will be much higher in D2 than in D1. So the reset current observed in D2 is much higher than in D1. So that's why the bipolar resistive switching can be obtained. For further electrical characterization, here is a D1. We also tested the D1 for 100 times, and we obtain average the rectifying ratio was larger than 10 to the power of 3 at the read voltage was 1 volt. And this will be useful to suppress the sneak path leakage. And also in D2, you can obtain from the right figure the robust retention at a relative lower, that says 500 nanoampere CC level can be achieved, and with quite a large memory window. Okay, let's come to the conclusion. This is the first time bipolar resistive switching is shown in flexible silicon oxide-based cross-point RRAM. And in the RRAM we show here, the robust retention with a large memory window and at a lower CC level has been demonstrated. And also the reference device, which is without the interfacial layer, it has a quite a large rectifying ratio, which can be used as a selector in the 3D cross-point architecture. And we also investigate the conduction mechanism in both D1 and D2. We show here the Schottky emission should account for the LR state conduction. So that's all of my presentation. Thanks for your kind attention, and I'm open for questions now.